let's prove the reflection property for the ellipse. Remember, the property that we think we noticed just by sketching is that a ray coming from one focus of an ellipse and bouncing off of the reflecting off of the ellipse will be reflected directly to the other focus. So let's see if we can prove this. To get started, let's name all these points. So let's call the focus on the left F1. Let's call the focus on the right F2. And this point down here on the ellipse, let's call that P. And keep in mind, of course, that that could be any point on the ellipse, right? So what we're going to do is the distance from P to F2, we're going to continue the line from F1 to P the same distance as the distance from P to F2. So about like this. Okay, this gives us another point down here. Let's call this, I don't know, let's just name things alphabetically now. Let's call that A. So we've set things up so that P is on the line from F1 to A. Right, so from F1 to A is a straight line. There's no bend at P. And then the second thing is that the length from A to P is equal to the length from P to F2. Okay, the next thing we're going to do is bisect the angle F2 to P to A. So when we bisect that angle, we get this line here. Okay. So we know that this length from P to F2 is equal to this length P to A. Because we have bisected this angle from F2 to P to A, that means this angle here to the bisector is equal to this one below the bisector because it's a bisector. Okay, so you might notice on this diagram that it appears that that this bisecting line that we have constructed is tangent to the ellipse. And in fact, that's true, and that's kind of the important thing, because if we can prove that this line is tangent to the ellipse, then that means that this angle to the left is what should I call that angle? Let me call that angle not Q, M. If this angle bisector is tangent to the ellipse, then that means that the angle M will be equal to the angle N here, because they are vertical angles. They're angles across from each other on the intersection of two lines. But then we'll be done, because that means this incoming angle M will be equal to the outgoing reflection angle to the right here. So all we really need to prove now is that this bisector is tangent to the ellipse. All right, well, to show that it's tangent to the ellipse, first of all, it has to go through the tangent point P, which it does, because that's part of how we constructed the bisecting line, right? This bisecting line L. So let me name the line L. So it has to go through P just because that was part of how we created the line L. The next thing to show is that no other point on the ellipse is on this line, right? So let's see. Take any other point on this line. Let's call that other point I. And let's ask, can I be on the ellipse? Okay, so to check if it's on the ellipse, all we need to do is check if the point I has the characteristic property of the ellipse. So we'll take the distance from F1 to I and add that to the distance from I to F2. So from F1 to I, we're going to add the distance from I to F2. Okay, well, because this line L bisects this angle, the distance from I to F2 is equal to the distance from I to A. So this F1 to I we're going to leave alone, but the distance from I to F2, that's the same as the distance from I to A. Okay, because this is an angle bisector. All right, and now notice that we have a triangle here. We have from F1 to A, from F1 to I, and from I to A. And two of the sides of this triangle we have sitting right here, from F1 to I and I to A. But one characteristic thing about a triangle is that if you add together any two sides, the sum has to be longer than the third side. So F1 to I plus I to A, that has to be a larger sum than from F1 to A. This fact is called the triangle inequality. So two sides of a triangle have to add up to more than the third side. Otherwise, they wouldn't make a triangle. Okay, but F1 to A, remember F1 to A is, so now I'm going to work on this F1 to A right here. F1 to A, that's the distance from F1 to P plus the distance from P to A. But remember, the distance from A to P is the same as the distance from P to F. So this is the distance from F1 to P plus the distance from P to F2. And now look what we have. We have the distance from F1 to I plus the distance from I to F2 is greater than, because of this inequality right here, greater than the distance from F1 to P plus P to F2. But P is on the ellipse. So the distance from F1 to P plus P to F2, that is the major axis of the ellipse. So what we've found is that the distance from F1 to I plus from I to F2 is greater than the major axis. But this means that I is not on the ellipse. Right? This means that the point I fails the characteristic test for being on the ellipse. Right? The distance to the foci was supposed to add up to the length of the major axis, but it was too long. So that means that no other point on this line is on the ellipse except for P. That means that L is tangent to the ellipse. And since L is tangent to the ellipse, that means that these two angles are equal to each other, and that is the reflection property for the ellipse.